Hello and welcome to HCI 509, Research Methods and Statistical Analysis. This lecture, Lecture 15, will talk about the chi-squared test. So let's get started. First, let's go back through a review on what we covered in the last lecture. A study counted and categorized students by gender and by whether they carried a smartphone or not. What kind of measurement is this? Nominal, ordinal, interval, or ratio? Give you a second here. The answer is nominal. You can see that we can't imply any kind of order by their answers. There's certainly no interval or ratio involved, so the only possible answer here is nominal. The second question, a post-study survey assessed users' emotions regarding interacting with the evaluated system. A Likert scale was used ranging from 1, bored, to 5, very excited. What kind of measurement is this? Let me give you a second to answer. The answer is interval. It could certainly be nominal, but that would be a waste of information. There's certainly an order to it because we have 1, bored, and 5, very excited, so that implies some kind of order. But the range of values we can infer, and again, if you answered ordinal, there's certainly good reason for your answer. But we are inferring that the gap between each of those 5 points is equal, so it would be interval. It certainly wouldn't be ratio. So interval or ordinal are good answers, but interval in this case seems to be the best one. Now the third question. A study measures users' task completion time. What kind of measurement is this? The answer is ratio. Remember, ratio requires there to be a true zero or an absolute zero. And because we're talking about elapsed time, it is possible to have an absolute zero. It's not possible to have a negative task completion time. So we could say something like user A took 80 seconds and user B took 160 seconds to do the same task. So it does make sense that user B took twice as long as user A to complete the task. Now for the fourth question. A study asked users to rank 4 pointing devices from most to least favorite. What kind of measurement is this? And the answer is ordinal. Usually when we have ranked sets of items, they tend to be ordinal. We can't imply interval in this case simply because we don't know if we ask them to rank 4, the gap between the first and the second choice, the second and the third choice, the third and the fourth choice. So ordinal is the only one that makes sense here. Let's talk about the chi-squared test. First of all, let me talk a little bit about the chi-squared distribution, which the chi-squared tests rely on. So if you look here, you've got the chi-squared distribution with different degrees of freedom. If you see the one that has 8 degrees of freedom, it almost looks like a normal curve, but it's slightly skewed out towards the right. You can see it's got a long tail. But if you look at the ones with fewer degrees of freedom, it certainly has a very different distribution. So this is why the degrees of freedom play an important role in the chi-squared distribution. The chi-squared distribution is a special case of the gamma distribution, which is used a lot in inferential statistics. So when do we use the chi-squared test? When we have categorical data and we need to determine a relationship between the variables. So generally we have counts in different categories, and the chi-squared test is usually the one that we as researchers rely on when we've got categorical data. We use contingency tables, which are how the data is normally presented. Now, a contingency table could be a 2x2 or a 3x3. We'll see some examples here. These are also called tables of counts. And they could be a simple 2x2 table, or you could have 10x10. The chi-squared test is probably the most popular significance test when we analyze frequency counts. Now, keep in mind there's two separate chi-squared tests. There's goodness of fit, and there's also independence test. Let's go through an example here. A study investigating the impact of age on user preferences towards two target selection devices, a mouse and a touchscreen. Two groups of users are recruited. So we have two devices and two groups. 20 adult users who are younger than 65 and 20 adult users who are 65 and older. So after completing a set of target selection tasks using both the mouse and the touchscreen, the participants specify the type of device they prefer to use. So here might be a chart that results. So we have age along the left margin, where we have less than 65 and 65 and older. And you can see here that the preferred device differed between these two groups. But is it a significant difference? So this is what we call a contingency table, where you have two different variables. One is the age of the user, and the other is the preferred device. And you can see here that easily the ones who are under 65 preferred the mouse, whereas the older or more senior participants preferred the touchscreen. So is this by chance, or is there really a relationship between age and the preference for a particular pointing device? So we run a chi-squared test, and this gives a chi-squared value and a p-value. So this can help us determine whether the result is significant or not. So that x is really a Greek letter chi, and we have the squared, so that should be a chi-squared. And you notice the 1, which means we have 1 degree of freedom. We get a value of 10.1, and then this gives us a p-value of less than 0.005. This suggests that the probability of the difference between the columns and the rows occurring by chance is less than 0.005. And if we go back and look at that, you can see here that we see there's a clear distinction between how those 20 users that were less than 65 and those that were over 65 chose their preferred device. Let's talk a little bit about the degrees of freedom in a chi-squared test. So this is calculated by the number of rows, -1, times the number of columns, -1. So we had a 2x2 contingency table just now. So it would be 2 minus 1 times 2 minus 1, or 1. And if you remember, the result we just saw had 1 degree of freedom, and that's why. And here's that calculation. So if we have 3 rows and 3 columns, the degrees of freedom would be 3 minus 1 times 3 minus 1, or 4. So here's a 3x3. And in this case, what we're doing is we're expanding the previous study. 3 different pointing devices, mouse, touchscreen, and stylus. We also include children. So now we have 3 task conditions and 3 participant groups. And we have a 3x3 contingency table. And you see the results in terms of what each one preferred. So the chi-squared test result is chi-squared and then 4, because we have 4 degrees of freedom, equals 16.8, and that gives us a p-value of less than 0.005. So this suggests that there is a significant difference among the 3 age groups regarding preference for these 3 pointing devices. Here's a table that talks about 2 different chi-squared tests. We often hear about the goodness of fit test, but there's also a test of independence, what we saw. With a goodness of fit, there's just one variable. You're deciding whether that one variable is likely to come from a given distribution or not. An example might be, we try to decide if bags of candy have the same number of pieces of each flavor or not. So maybe you have M&Ms or Jolly Ranchers, and you break open a bag, or you actually broke open several bags, and you count the number of flavors and each bag. And then you try to see if those bags have exactly the same number of each different flavor. So our hypothesis might be, our null hypothesis is the proportion of flavors of candy are the same, and our alternative hypothesis is that the proportions of flavors are not the same. So it's the opposite of the null hypothesis. Remember that mutual exclusivity that we need to maintain. The distribution we're trying to check is the chi-squared distribution. And then the degrees of freedom is the number of categories minus 1. So it'd be the number of flavors of candy minus 1. Since we're only working with one dimension, if we have 5 flavors, the degrees of freedom would be 4. The chi-squared test of independence is the one we just went through 2 examples with. We're trying to decide if 2 variables might be related or not. For example, we want to decide if moviegoers' decision to buy snacks is related to the type of movie they plan to watch. So our null hypothesis would be the proportion of people who buy snacks is independent of the movie type. The alternative hypothesis would be the proportion of people who buy snacks is different for different types of movies. This is looking at the theoretical distribution of chi-squared. And the degrees of freedoms would be the number of categories for the first variable minus 1, multiplied by the number of categories for the second variable minus 1. Remember, we saw that just now. And in this example, if there's 5 different movie categories, we'd have 4, and then the snack purchase would be just a yes, no, so it would be 1. 2 minus 1, because yes and no is a dichotomous variable, and 2 minus 1 is 1. If we have 5 different movie categories, the degrees of freedom for this would be 4. We talked about the assumptions when we had parametric tests, but the chi-squared is not a parametric test. It's what we call a non-parametric test. But even so, there's certain assumptions we have to maintain. Non-parametric tests are not completely assumption-free. So we have 2 assumptions we have to satisfy in order to use the chi-squared and have some confidence with our result. First of all, the data points in the contingency table must be independent of each other. So we can't have a participant who prefers both the mouse and the touchscreen, because then the rule of independence would be broken. Also, we have to be careful of sample sizes. With a smaller sample size, it's very difficult for us to determine whether it's following the chi-square distribution or not. So we hear different numbers, but 20 or larger is what our textbook says. I've heard 25 or larger and 30 or larger. Obviously, the larger the sample size, the better and more confident you're going to be with your result. Now let's talk about the chi-squared test on JASP. And with this, I've got a couple of JASP inputs that I've posted to this lesson. So here we need to select the method. Notice that I start with this contingency table, right? So this is the contingency table we talked about with our first example. And you look at frequencies and contingency tables, right? So this would be under the classical, not the Bayesian. So we would load the CSV file, and again, we provided a CSV file for you here. Then you go to frequencies, select contingency tables, and if the table looks like the one in the examples, it's really going to cause some issues. So remember, we have mouse and touchscreen as our column headings, and then for age, we have these 2 here, and you can see our values are 14, 4, 6, and 16. Now, if you look over here, when it builds our contingency table, it says mouse 4 and 14. And this is very different than the contingency table we saw before. So we can't use data in this format when we bring it over from Excel or your favorite spreadsheet. Here's how we want to do it. We want to provide the raw data, which is also provided with this chapter. And this breaks down each of the 20 participants, or actually 21, their age, and also the preferred device that they have. This is in row format, and you can see here that this raw data is what we need in JASP. So it actually generates the contingency table from this. And so when we feed it that information, we would get a contingency table over as you see on the right. Notice we have participant, and then the rows would be age, the columns would be preferred device, and you can see here it's generating a contingency table much like we would expect. You can see the chi-squared test, the value is 10.101, degrees of freedom is 1, and the p-value is pretty small. Notice that the degrees of freedom does not depend on the sample size, but on the number of rows and columns for this test of independence. Thank you, and I hope this has been informative. I'll see you next time where we talk about additional non-parametric tests.